Hey everybody, this is Troy from the Do-It-Yourself World Electronics. Been a while since I posted a video. I've been busy on processing and selling firewood, my main source of income these days. But I have been working up in my lab right now, taking a little rest, and I got a really interesting thing to show you here. Over here, I have a coil with 3 wires wound together in parallel. The primary wire, actually, there's a 20 gauge and there's 2 18 gauge wires. The 20 gauge I'm going to call the primary, the thinner wire. I have a desktop power supply here going through an electronics switching device and rapidly pulsing power to the primary coil at a high frequency. And I'm collecting the back EMF and the spike, voltage spike, through a transistor and into a battery being charged. So this is just harnessing the back EMF and voltage spike from a collapsing magnetic field in a coil. Just basic science here, nothing special. Primary wire being pulsed. Over here I'm showing 0.042 amps, 0.5 watts at 13.73 volts. I was trying to simulate an average 12 volt battery. So what's important here to notice is 0.042 amps. Now, one of the other wires, one is not connected. Another one with the white lead here, let me make sure I've got the right one. This wire here, this is the 18 gauge wire, a second coil, which is not connected to the power supply at all, is going through a bridge rectifier to another set of batteries which are junk. And they're taking a charge, sitting at 14.4 volts right now. I'm using jump batteries because it shows they're really bad batteries, so they show a massive jump in voltage when any change occurs. If I disconnect them, they drop rapidly. If I connect them, it actually shows a charge clearly, which is good to see. Right now it does not like the meter, so the voltage is dropping a little for some odd reason. But anyway, this second coil is just coupled to the first coil magnetically. And when I pulse the first coil, the second wire is also getting a pulse. It's like a transformer. And I'm collecting the collapsing field, the resulting spikes, and putting it through this battery bank. Now what's interesting, again, it's not electrically, physically connected to the power supply. But when I disconnect, this is the cool part. Let me zoom in on the meter here on the power supply. Right here, 0.042. This is what's important. I'm going to disconnect the coil, the secondary coil, which is charging these batteries, and watch that change. The current goes up and the watts go up. Disconnecting the secondary coil, it's using more power. So I've actually disconnected a load. The battery voltage is dropping rapidly, showing that it is disconnected. Oops, you don't see that. The voltage is dropping rapidly. The batteries are disconnected. And I'm using more power with one coil and a reduced load. That is interesting. Let me reconnect the second coil to the second set of batteries. Make sure I get the right lead here. Connect the bridge rectifier to the second coil. The power used goes down. We're back to 0.5 watts. My batteries are taking a charge. I have connected a load to the secondary coil and actually am using less power. Isn't that cool? So to reiterate, connecting with a 3-coil essentially transformer, 3 wires connected together, 2 of which I'm using. If I'm pulsing one, it uses, was it 0.049 amps, 0.6 watts to run the electronics and pulse the coil. And the voltage, the collapsing voltage spike is going into a battery. But if I connect another coil to charge a second set of batteries through a rectifier, the current goes down. It uses less power. That is crazy. Now I've got a 3rd coil, which I'll be experimenting with later on a separate video, but I need to clean up my bench. This is a mess. So stay tuned for some more exciting and cool experiments to come. I'll talk to you all later. Please do like this video. Subscribe if you haven't.